Hi everyone and welcome to this math vlog and permission of letting this math vlog be a language of humanity. Okay, so each human person deserves to live with dignity while staying humble and curious. Yes, each person is like a star in that very big galaxy. So it is so tiny, so that's why even if we have a lot of accomplishment and what have you, we have to remain humble because we're just a tiny star. But as a tiny star, we are so important, okay, for the completeness of that big galaxy. So we have to feel that indeed we deserve to live with dignity, and hence all of us deserve to live with dignity. So join me and let us make time for curiosity by celebrating math stories around conics. Alright, so again, a conic is just an intersection of a plane like this, the green one, the green plane, and the cone, alright, the blue cone here. Okay, and the kind of conic section that we'll be getting will be depending on the angle of the plane in respect to the cone. Okay, so in this case, it's like you are having a circle, right? Okay, and again, the instance of a conic section, either a circle, an ellipse, a hyperbola, or parabola, will be depending on the angle of the plane, okay, in respect to the cone. Okay, so here we have in the build of our author Juan Ponce, Campuzano. Okay, so beautiful build here. So you have an angle. Okay, so at 0 angle you have a circle. So let's increase the angle, let's change the angle. So at 25 degrees you have an ellipse. Okay, let's increase further the angle. Okay, at 50 degrees you have the hyperbola. Okay. And at 155 degrees you have a parabola. Okay, and there's also an instance wherein the intersection will not be classified as a conic section, but it is just a vertex. Okay, this one you have the vertex or the apex. Okay, or a line. There you go. So this we call this one as the generator, the vertex or the apex, and the generator. So these are not conic sections, okay, but that is an instance of the intersection of the plane and the cone, where you're getting the vertex and the generators, the lines, okay, the intersecting lines that represents the corner, the corners of the cone. And let me have this short insight. Okay, so our math legends had the capacity and resources to define and quantify all of the elements of geometry for good measure. And yes, it's true that up to this day we have some curious minds, and it is good that these curious minds would know that they don't have to start from scratch and answer their questions. They can discover the documentations of these math legends and celebrate the reality that almost everything, not really everything, but big part about the universe has been scientifically defined and quantified already, so that any math lovers and math enthusiasts will be guided in their discoveries, and that way we can keep the culture and the heritage of math discovery to live on. And you might be wondering, when did the descriptions around conics and the study about it all started? So let's go back then to the time of Menaechmus, around 350 before Christ. Menaechmus is a student of Plato and Eudoxus, and he is also a tutor of Alexander the Great for such subject matter. And you know why? Because conics has an application for scenarios at wartime. The study of conics was used in solving the problem doubling the cube. Okay, as you can see in the background, we have here the Apollo, or the Oracle of Apollo. So this is very, very relevant to the story of the doubling the cube problem. And this is a UNESCO site. So according to Eratosthenes, there was a plague, okay, a long time ago, okay, here. And then they consulted the Oracle of Apollo, and the Oracle of Apollo instructed them to double the volume of the altar. Okay, so for example, you have the current volume of the altar, you just have to double the size, double the volume of the altar, and that would solve the plague. You might think that they are being superstitious about it, but actually the Oracle of Apollo is challenging the mathematicians, the scholar at that time, never to neglect, okay, the progress of man, okay, and to make it as elegant as ever. So they are challenging the math legends and the math scholars at that point, at that time. Okay, so in solving the doubling the cube problem, or the Delian problem, they have not able to find the answer using just the ruler and the compass, because you know the Euclidean geometry is two-dimensional, and they came across functions that are three-dimensional. Okay, so you think that in doubling the side lengths, you are now doubling the volume of the cube. That is wrong. The answer to that solution of just doubling the side lengths, okay, is a ball later than the expected answer. Okay, and now we will be discussing some of the solutions of the Delian problem. And we already have some GeoGebra builds, we have some documentation via GeoGebra, so I will going to give you a technical walkthrough on that documentation. So join me. Alright, so the first solution that we'll be discussing is the solution of Menaechmus. And this GeoGebra documentation has been or was prepared by dear Yin Bon or Albert. Okay. So again, Menaechmus is a Greek mathematician, and he's very famous on his discovery for conic sections, or discovery on conic sections. So he was the first one to show what is an ellipse, parabola, and hyperbola. Okay, and this was the study of the conics, or what is this? What kind of function is this? What kind of graph is this? You know, I mean, let us put ourselves in the shoes of the math scholars before, math legends like Menaechmus. Like, they discovered something new in the field of geometry for good measure. They saw an ellipse and they don't know what that is, so they have to define it, they have to study it, you know. So he was the first one to describe what an ellipse is, parabola and hyperbola, and he encountered it when he tried to answer the Delian problem and using the main proportionals problem. Okay, so let's discuss it. Okay, so what are the variables here? So we have a, b, x, and y. So a and b represents the volume. So a as the initial volume, b as a target volume, and then x and y as the side lengths. Okay, so we have this first expression here. So let's discuss it together. So basically, if you have a side length of x telling us that the side length of x is proportional, of course, to the volume. So there's a relationship on how long is the side length, and that would make the volume big. If the side length is short, then the volume will be much smaller. Okay, and this one also, it's telling us that side length x, the initial side length x, okay, is proportional as well to the side length, the target side length y, wherein that side length y, okay, is proportional to the target volume, and that's double the initial volume. So A and then 2A, and 2A will be represented by B. Okay, so we have to define the proportion of the initial side length, okay, with the target side length that contributes to the target volume. Okay, so the bridge there is the proportional between the initial side length x and the target side length y. Okay, and I have prepared a GeoGebra presentation here, and we can be inspired by this photo of the Oracle of Apollo. It's a UNESCO heritage site, and it's a reminder to all scientists and math enthusiasts and lovers that we should not take for granted any math discoveries, math problems, and scientific problems like climate change, right? So we, as one global family, we have to work together, okay, to ensure that we can use math, we can use data science to ensure that our Mother Earth, our planet Earth, will be protected, okay, will be healthy for the many more generations to come. Okay, so we have these expressions here from this one, general expression. We break it down, and then we make some derivations. Okay, so we'll now be discussing, okay, and breaking down this general expression into 4 specific expressions and specific proportions. Okay, so we have here initial volume A is proportional as well to the side length x, and again, as mentioned a while ago, that the initial side length is also proportional to the target side length that would lead to the target volume. So if we will know, how longer the target side length is for us to have a volume double than the initial volume. Okay, so upon determining the proportion of the initial side length, the target side length, we would be able to construct an altar, okay, that is double the size of the initial altar. Okay, so we will going to manipulate this expression here, so we will just cross multiply. So A times Y is AY, and then X times X is X2. So we now have this equation, X squared minus AY equals 0. So we'll park that. We have another equation here, our proportionals here. So X is to Y equals Y is to B. So cross multiply again, we have Y squared equal BX. Again, another proportionals. We have X is to Y equals Y is to B, and then cross multiply, we have XB equals Y squared. And the last one, A is to X equals Y is to B. Cross multiply, we have AB plus XY. So we just basically, the representation of this one, the proportion, is like ratios, division, how big or how small one entity is from the other. When we compare two values, then we can divide, so we can have ratios here. Okay, and we'll be making use of these equations here. We're going to graph it. And now that we have the functions here, x squared minus ay equals 0 and y squared equals bx, then we can somehow try to graph it. Okay, so Albert already have this in his documentation, the graph of x squared minus ay and y squared equals bx. Okay, and the intersection of those two parabolas, okay, will now give us the initial side length and the target side length, the x and y. So I'm going now to show you how to prove that with this kind of solution, having the graph of x squared minus ay and y squared equals bx, and then in the intersection of it as the solution to the mean proportionals is correct. So I'll demonstrate, okay, on how correct it is. So for example, we have an initial volume of 2.5, okay? So the double of 2.5, so 2.5 times 2 is 5. Okay, so this is now our parabolas, and you have also the hyperbola. Okay, so we'll consider also the point of intersection A has the initial side length and the target side length, x and y. Alright, so we were going to get the calculator, okay, and we will compute the volume, okay, considering those side lengths. So 3.15, so 3.15 times 3.15 times 3.15, so we have 31.25. Okay, so let's part that. So we'll get a notepad here. We'll note it down, 31.25. And we'll now be getting the volume of for the cube with a side length of 3.97. So 3.97 times 3.97 times 3.97. So we have 62.57. Okay, so 62.57. And let's see if we are able to double the volume. Okay, so the initial volume is 31.25. 31.25 times 2 is indeed 62.5. Okay, approximately 62.5. Alright, so then we can say that the elegant solution of Menaechmus, okay, managed, alright, to solve the Delian problem. So please stay tuned. We will then be discussing more about the solution pertaining to double mean proportionals. And now we will discuss a little bit further the double mean proportionals. We have here another Greek mathematician, Hippocrates of Chios. And yes, he has a lot of influential work on three classical problems like the Delian problem, okay, the double mean proportional. So let's interpret it. This is the build of Albert, Yin Bon. Okay, so again, we have this general expression of the double mean proportionals. So I had discussed that a while ago on how to interpret it. And as always in math, we try to have an example at the simplest form. Unit equal to 1. Okay, so for example, our initial volume is 1. So in here, in this build, the initial volume has been represented by B. So B equals to 1. And then we double the volume. So 1 times 2 is 2. So the target volume is 2. So we were just going to substitute. So A is 2 and B is 1. So to the general expression here. A is to X equals A is to Y equals Y is to B. And we were going to represent that as ratios. So we have the one here. So 2 is to X equals X over Y plus Y over 1. And we do the math there. So we cross multiply and what have you. Cancel out X here. Okay, so you have 2 equals Y squared. And then, since 2 is equal to Y cubed, so simplify Y, we have Y is equal to a cube root of 2. So the target side length has been represented by the number cube root of 2. But at the time of Hippocrates of Chios and Euclid and Menaechmus, okay, they are defining good measure using Euclidean geometry. It's two-dimensional. So they had some difficulty on how to construct cube root of 2 using a ruler and a compass in a sandbox. And they just can't construct cube root of 2. Okay? And thanks to Menaechmus, he discovered parabolas, and as mentioned in his solution a while ago, that the intersection of the two parabolas by using some derived expression from the double mean proportionals, we have managed to use the intersection to extract or to determine the X and the Y. In other words, to determine the initial side length and the target side length. Okay, so this is really a very classical problem, Delian problem, and we have discussed an amazing classical solution to that challenge of the Oracle of Apollo, never to neglect math discoveries and math problems. So please stay tuned. We'll be discussing some classical application as well on conics. This math blog is based from a beautiful article of Britannica. Thank you so much, Britannica.com. Now we will be discussing some classical applications of conics. So let's start with the contribution of Diocles. Okay, last 200 before Christ. So he demonstrated that geometrically, that rays, for instance, from the sun that are parallel to the axis of a paraboloid revolution. A paraboloid revolution will be produced by rotating a parabola about its axis of symmetry. So you have the isometry, and then you have the paraboloid revolution there. And he demonstrated that the rays that are parallel to the axis will bounce back towards a common point called the focus. So like this one. Okay, so the focus point here is the meat. Okay, and then that's the another example of applying this behavior, okay, of some rays that bounce from a paraboloid of revolution. So they bounce back towards a common point, the focus. And then the beautiful architecture asset. Okay, so we have a beautiful architecture asset at Hagia Sophia Cathedral in Constantinople. Okay, and this was cited by Atemius of Tralles. Okay, so he's one of the architects of the Hagia Sophia Cathedral. Okay, that was completed in AD 537. Okay, so here the problem is the requirement is to make sure that an altar in this beautiful cathedral will be lighted by the sun. Okay, so we're also considering sun rays here. So you have an ellipse in the cathedral. So the focal properties of an ellipse has been considered in determining the position, the coordinates of a particular altar to make sure that at any time of the day an altar will be illuminated. So as you can see here, we don't know what time of the day we have in this picture. So you have an ellipse there, and then the sun will going to touch one part of the ellipse, then the ray will bounce back to a certain point, okay, where you have an altar there. So the focus of one intersection of the sun ray and the ellipse, okay, will produce one focus, okay, and that one focus then you can have the altar. Alright, so it's a beautiful architectural asset here. It's also a heritage site. Okay, so there's math in this cathedral, the Hagia Sophia Cathedral. And we also have some post-Greek applications outside optics. Of course, we have to mention the law of planetary motion, that the planet travels in an ellipse. Okay, it's not a circle, but in an ellipse with the sun as one focus. And also, Galileo Galilei published the first correct description, okay, of the path of the Gentiles, a parabola, okay, in his dialogues of the two new sciences. Some of this application might be new to you, so in the next episode we'll be discussing in more detail this application so that we can touch the properties, we can appreciate the properties of each conic: circle, an ellipse, parabola, and hyperbola. So thank you so much for joining me up to this point, and I'll see you in my next vlog. Bye!